good afternoon. Thank you all for attending this panel today. My name is Maria Gomez. I use she, her pronouns, and I am currently working with the Institute of the Environment, Duluth, in this panel series. So thank you all for being here. This semester, we're putting together panels related to the 17 United Nations Sustainable Development Goals, or SDGs. So it is so important that the conversation and action around the sustainability goals continue in our university. So I want to thank you all for allowing us to bring these conversations into your classrooms, and for all the panelists to be joining us today. This project is funded by the IonE Twin Cities and the Rapid Response Grant through the GPS Alliance. And just a little reminder that this conversation has live captioning and will be recorded and then posted on the IonE Duluth website for future academic use. And I would like to put in the chat the land acknowledgement for the University of Minnesota, because I think it's very important that we acknowledge that we are situated in traditional and ancestral indigenous lands. So with that being said, I'll turn it over to Andrew, who's going to do the introduction for this panel.
Nice to meet you. I'm Andrea Schocker. For those of you who don't know me, I'm the head of civil engineering here at UMD, and really excited to welcome this panel, and for Maria for putting this together, and IonE for hosting these great discussions. So I'm going to give just the facts so we can get going on the real discussion. Our first panelist is Dr. Sarah Billington, and she's professor of civil and environmental engineering at Stanford University, and happens to be a good friend of mine who I didn't know was going to be on the panel. So that's exciting for me. And I don't know if Rob's going to get here in time, but Rob Gradoville from the Institute on the Environment at the University of Minnesota is an impact coach, portfolio manager, designer, and engineer. We have David Williams, who's the lead MEP engineer and sustainable design specialist at LHB here in Duluth, Minnesota. And Dr. David DeZombach, who's head of civil and environmental engineering at Carnegie Mellon University. Dr. Boya Xiong, who's an assistant professor of civil, environmental, and geoengineering at CSE, which is the College of Science and Engineering at the University of Minnesota Twin Cities, and Dr. Jessica Kaminsky, who's an associate professor of civil and environmental engineering at the University of Washington. And one great thing about COVID, I know there's a lot of bad things, but as we get opportunities to have some virtual panels that we never thought about doing this way before, you've got some of the top experts around on this panel. That's super exciting. So I'm going to turn it over to you guys. All right, Maria, are you the questioner?
I think I'm not.
Dr. Johnson, are you the questioner?
I think I maybe did have the first question. So the first question for the panel.
Let me interrupt real quick. Were people going to go around and just quickly say, you know, what they study, what they do? So maybe
right. The 1 minute.
You want to call off names?
Yeah, sure. Go ahead, Sarah.
I could start. Yeah, great. Thanks. Hi, everybody. Thank you so much for having me. And I was also so excited to see that Andrea was going to be introducing me. So I'm going to take a little extra time just to say we used to go to conferences all the time together. That's where we would meet, our biannual conference, and vent about being the only women and, and being an assistant professor. And but it was a lot of fun, and I'm so happy to see you here, Andrea.
You too.
Okay, so I'm at Stanford, and I have worked in a lot of different areas that cross with sustainable engineering. I think you can think of sustainability as being related to like economic sustainability, environmental, and social. And I realize I've sort of touched all of them a little bit. For the past 20 years, I've mostly been working in materials, so cement-based materials that are very durable and last a long time, that can save money on maintenance, and then bio-based composites that have a closed loop life cycle. So they biodegrade into a product that is used to remake them. So that was a very environmental thing. And now I'm actually very focused on social sustainability, and I work on how the built environment is impacting our well-being, and also have a focus on affordable housing acceptance, and how the built environment can be designed to increase that. So that's my intro.
Great, thanks, Sarah. I guess David next. David W.
Yeah, I got it. You know, I was a campus brat around UMD because my dad taught at UMD from 1966 on. So He taught in the music department, so I spent a lot of my formative years wandering around the halls when there was much less of a campus. I ended up going to MIT in Boston. At the time, we didn't have all these wonderful interdisciplinary programs you guys are doing. So we had a thing where you could design your own degree. So I did a design your own degree that had architecture, civil engineering, urban planning, and some mechanical engineering all involved in it. Came back to, and I was very interested in solar energy and alternative energy. And of course, 1981, you know what? There was none of that around. So I ended up going into both the industrial market that we have here, plant engineering, and then went into architecture and engineering. The latest firm I've been with for 28 years, LHB, is a leader in sustainable design in the upper Midwest. And I've been kind of leading a lot of the effort on the engineering side of our business because we have architects and engineering. We leave the civil engineers a little out of that a little bit, but actually they've been really good on water control issues. So I've been doing this a lot of years and was involved in the Minnesota State Sustainable Building Guidelines, which is one of the things that we use in the state of Minnesota, not only to make buildings better for the state, but also to track their energy performance. So thank you.
Great, thanks, Dave. Actually, I think we do have Rob. Rob G is here too. I can't see him in the sea of names, but
I'm here. Yep. Yep.
Yeah. Okay.
Can you hear me?
Yes.
Okay, cool. Yeah, hi everyone, I'm Rob. I feel like I'm the fake engineer of the group. I have engineering degrees, but I don't know if I'm an engineer. My story is I studied mechanical engineering. I grew up on the East Coast. I'm actually a transplant to Minnesota. Studied mechanical engineering, ended up joining the Peace Corps. I spent 2 years living in the Dominican Republic, designing and building water systems in a village. Kept kind of doing that while going back to grad school. I started a PhD and found out real quick that was about going deep in a specific topic, and I'm a connector, so the PhD didn't work out for me. But I ended up kind of continuing on this. What does it mean to be a professional kind of Peace Corps volunteer? And so I spent some time in Cusco, Peru, studying how water resource management practices were having to change due to the effects of climate change high in the Andes. And then I spent the past kind of decade between a couple of nonprofits, first at water.org, kind of the Matt Damon charity, if some people know it because of that, founded by a WASH engineer and then co-founded with Matt Damon. And so expanding partnerships for the financing side of the water and sanitation crisis globally. I was working a lot in India and then some in Africa and South America too. And then kind of the past 5 years, I was with the social impact arm of a design consulting firm. It was called IDEO.org. I was based in lots of different places, but I was the portfolio manager for a series of innovation challenges where we were sourcing new ideas from social entrepreneurs around the world that involved, sometimes product design, sometimes engineering, sometimes new programs and services, and kind of proving them out over the course of a year and a half and sending them off in the world to do good. And the end of my story is that I did that. I spent my last year at IDEO.org in Nairobi, helping them open their Nairobi, Kenya, opening their first international office. And then my wife and I, it was good timing. We quit our jobs and we hiked the Appalachian Trail and it was incredible. We did a through hike. It was a 6-month experience. And so that was the tail end of 2019. And we said, let's go back to Minnesota where we lived before and get back to normal in 2020. And it did not pan out the normal that we were looking for, but happy to be here.
Thanks, Rob. Dave D.
Hello, everyone. My name is Dave Dzonbak. I'm professor and head of civil and environmental engineering at Carnegie Mellon University. My work is in water quality engineering and sustainable water resources. In recent years, since 2014, we have a strategic initiative in the department here focused on climate change adaptation for infrastructure. And I've been engaged in several projects related to that. We think that's a very important area for our field of civil and environmental engineering, and we have stood up a number of courses and have a number of research projects going on in that realm.
Thanks, Dave. Boya?
Hi, everybody. My name is Boya. I am a new assistant professor in the Civil, Environmental, and Geoengineering in the University of Minnesota Twin City campus. Really honored to discuss this really important matter with everybody else, with such a diverse experts who works on all different aspects of sustainability. So I, as a new faculty, my research for the past few years is primarily, I think, fall under the large category of environmental organic chemistry and the fate of contaminants in aquatic systems. And primarily, I look at macromolecules and polymer chemicals and materials, such as including microplastic and nanoplastics that are currently poorly understood. And I think these function of these materials and chemicals are really important, but and the use of them kind of shaped our modern economy, but we've been using them without really thinking about their environmental impact. So my lab is trying to understand their physical and chemical behaviors when they're accidentally released to the environment, when they contaminate our water systems, and the risk associated with it. So I think the way that my work is related to this panel is that we overall has a mission to enable sustainably, environmentally benign design and selection of polymer materials at the first place, and hopefully a future without pollution and waste.
Thanks, Boya. And Jessica?
Hi, everybody. Jessica Kaminsky. I'm an associate professor at the University of Washington on civil and environmental engineering. I really appreciated the way Sarah introduced her work. So I do all of my work in social sustainability. I'm very interested in infrastructure services for vulnerable populations, which means I'm often, though not always, thinking about sustainable development goals and global infrastructure projects. So, for example, we've looked at mass migration of refugees and asylum seekers and what that means for housing and urban environments. We've looked at the correlations between getting toilets in schools around the globe, what that means for test scores and student attendance. More recently and more locally, we've been looking at things like how behavior change from social distancing has impacted the technical performance of our water infrastructure systems. I'm also a mom. I have 2 small kids, which has significance for interest in working in global projects, right? Being on the road. So I'm also happy to talk about that if anyone wants to talk about that side of it. Thanks for having me.
Thanks, Jessica. Okay, I guess, Maria, we're ready for the questions now.
Yeah, I think we are, and I think Mary or Alison are going to ask the next question.
Okay.
Okay, so actually, Nate, I think that you had the first question, but I'm happy to give it.
Okay, very good. No, I have it. Go ahead.
No, go for it. It's fine.
All right, I have it right here in the chat. I'll put it in the chat too, actually. It says, how do you plan into your designs or your design strategies the ability to handle the climate that we're currently seeing and future changes that are predicted? So here it comes in the chat, but I think we're just hoping to facilitate a discussion about what does it mean to plan ahead sustainably in light of climate change.
Well, I can offer some work we've been engaged in for the past couple of years, and that is looking at short-term, near-term, 1 to 20 year forecasting of climate conditions in specific locations. So this is something that's challenging to do with global climate models, and we've been looking at using historical data records for specific locations where real projects take place in specific locations, and there are many, but not all locations have long-term data records. So we've been engaged in work looking at how one can make projections from long-term data records and what portion of that data record to use and what kind of projections it provides and how accurate those are. looking at testing against backcasting against some actual data. And also coupling these statistical data focused approaches with global climate models, downscaled versions of global climate models. We think this set of tools is something that all civil and environmental engineers are going to need to become familiar with in, now and in the years ahead. And so we're spending some time working on that.
So I might say quickly that I'm less interested in changing designs for adaptation and more in using infrastructure as a tool to fight climate change and reduce emissions, right? The built environment is a huge, massive collective system that we all use. So structural changes there are an enormous tool in the fight against climate change. So that's one part of the answer. The other part, I do have a couple of projects looking at water systems and climate change in remote Native Alaskan communities. One of the things we see there, right, in the Arctic, it's sort of a bellwether of what's to come because the climate changes there are more extreme than what we're experiencing, down here, for example, in the lower 48. And, just as Dave was saying, right, we see increased variability in what we expect. So of course we can accommodate that in designs, but one part I would emphasize, being the construction person, right, is that increased variability leads to increased operational complexity. That's a big problem for the people who are running our systems, particularly in rural and remote areas where people don't have the advantages of some of the more advanced educational systems. So designing for simplicity, despite that increased sort of natural complexity, is going to be a vital part of our work going forward.
And I guess I'll just speak a little bit to the building side of things when we're pouring concrete and designing our systems. Unfortunately, a lot of our system designs are related to things that are in the building code or the energy code, and so many of those are look back type documents. We use in the HVAC design industry weather data that comes from ASHRAE, the American Society of Heating, Ventilating, and Air Conditioning Engineers. Those are 10-year look backs. And it's very interesting to look. The new ones are published every 4 years, and you can watch in any specific weather data that increase in extreme temperatures and how often it happens. There are some tools that are out there that are able to be used for forward looking. There's some kind of modeled weather data that you can say you're going to assume a 2% increase in CO2 and 10 years out it's going to look like this. But for the most part, the practice doesn't use it. And we have this big battle between, the people that have been in the industry a long time and they've been doing it a certain way for a long time. And they're very resistant to change. And we're in the midst of looking at a new energy code in Minnesota right now. And the old school, what I call the old school engineers, even though I've got a lot of gray hair, they don't want to make that move to the latest and greatest, newest energy code all the time because it's more complicated and it's more likely to break down. And the systems you use are not the same as what we've used. So it's very difficult to move that inertia along. Now, we've had the luck in that our engineering practices in the HVAC area has been only as old as I've been with the company. So that's 27 years. So that means we've been able to be a little more agile than somebody that's been in the engineering business for 50 or 60 years. They just have a little more inertia involved. So we looked at thermal displacement ventilation as something that we could use in K-12 education schools. We've been doing it for over 20 years. Those systems will save 20 to 30% of your HVAC energy if you use them and implement them. But still, it's only the projects we're touching. We can do some publicity, we can do some speaking, we can do some journal articles, but the industry doesn't change that way. The industry changes by individual practitioners going out there and doing something different. So that makes it difficult to make kind of wholesale change in what we're doing.
I can kind of add on. I think Jessica was saying that she focuses more on kind of like how the built environment influences this issue, and not as much on the adaptation side. And I mean, what's interesting to me is kind of that flip, the adaptation. How are humans dealing with this experience? And so, you know, as engineers, we kind of try to start out all of our projects with what are the constraints, and the constraints are kind of unknown at this point. What are the constraints? They're changing every day. They used to be known, they used to be projectable, and they're not as projectable. So in designing solutions that will help people, you know, achieve the things we try to do in life, like be farmers and have industry and society and all those things, engineers play a role. There's much more variability. So making adaptive systems is super important, things that can be stretched when it breaks left and right of the assumed constraints. So that's one thing. There's a lot of talk right now in the sustainability field about going beyond what's sustainable. So like minimizing the negative impacts, but going to a regenerative approach where the way we interact in society actually rebuilds some of the natural environmental systems that have been degraded through the course of, you know, capitalism and just the humans living on this planet. So that's one thing. Regeneration is another thing. And then the last thing I was thinking was similar to adaptability, but as engineers and designers, thinking about what we put out into the world from a point of this is the prototype and it's going to evolve many times in the future. So I'm not trying to solve for every future case because it's probably impossible and I don't know the future cases. Just knowing that it's a starting point and it's meant to be evolved and built upon. That's kind of a new perspective, I would say.
Cool. I'll jump in. I've been taking notes because I could kind of connect to everything, which I really love. that we're all sort of working in very different areas, but there's so many overlaps. So I guess some work that I've done in the past was on with a climate model predictor. So a little bit related to what Dave was talking about, predicting like the weather changes and the climate changes, and then we were looking at corrosion of infrastructure on coastal environments, and when the temperature changes and different storms and things, the potential for corrosion will change as well, or the diffusion into the concrete and those kinds of things. And that was really fun. And the neat thing about that was that we were using a framework that was developed for earthquake engineering, and then we adapted it for durability and added on to that climate change. And it was so you can use a lot of the tools that are used in other fields to start looking at different climate change problems or adaptations. Let's see, I also really liked Jessica's comment about design for simplicity. One project that I'm working on with a colleague who's a wind engineering and computational fluid dynamics expert, she's very interested in natural ventilation. So that's something that we can do out here in coastal California. I'm not sure if David can design those for Minnesota, but it is a good option here, but some really interesting challenges. Well, one, definitely practitioners not being as familiar with how the systems work. And we live in buildings or we work in buildings when we're at work that are naturally ventilated, and there's a lot of goofy problems with them. So for the acceptance side. But there are also things like natural ventilation could be less dependent on the grid, which is great. If they're going to be blackouts or brownouts, I'm not actually quite sure what the difference is. And then also, though, we have wildfires out here in California. So then maybe natural ventilation isn't so good because of the smoke and dealing with the smoke. And so how much of a backup system do you need? Yeah, so that's another. And then I think the work that I'm doing related to affordable housing and acceptance is really important for the environment, because not just for the social sustainability, but also for the environment because of sprawl. So we're sort of consuming land much faster than I can't remember what the quote is, but the statistic. But the population is growing, and then we're consuming the land much more quickly. So that's sprawl. And that just puts so much demand on all of our natural resources. So there are definitely ways, certain densities of cities that actually are better for the environment and can reduce carbon emissions globally. And so finding that balance is really important. So affordable housing acceptance, like around here in California, what happens is people have to live farther and farther away. I actually have colleagues that commute like 2 hours to get to it drives us nuts and it's awful. Or they end up, some of the people are living in camper vans basically during the week. It's just awful. So we have to accept this density or densification, both for social reasons, but also for sure for the environment. And then the last thing that I'll mention is also kind of on behavior change, which designing, I'm working with some computer scientists and psychologists around designing interior spaces, so the physical and digital environment for promoting well-being. And the idea, one of the things that you can do is with sort of biophilic design, we're aiming to be promoting pro-environmental behavior, which actually has been tied to well-being and also would of course be good for the environment if it can do much. And also a sense of belonging. So we have found with some online studies that you can increase a sense of belonging depending on what materials you're using in buildings. And I really like that. I think that should help also, aiming a little bit Pollyanna-ish, but if we're all going to be living on top of each other a little bit more with densification, like trying to increase a sense of belonging for all different populations. Like we found it to be different for women and people of color. So it just adds a sort of a new interesting dimension to design. Thank you.
Okay, I think it's my turn. I want to add kind of onto some of the things that was touched on in terms of we want to also have predictions and forward thinking of the future climate, be able to predict what will happen. And I wanted to speak a bit challenge of how that can be a little bit challenging for the space that I'm working in. I think in particular, I think about climate change as many different aspects, as you've all mentioned, in addition to greenhouse gas, and there's also related to biodiversity and ecosystem health. And, for example, a more disturbed ecosystem may be more vulnerable towards climate change. So I think our work on studying the fate of chemicals and polymers is trying to inform risk assessment of these polymer chemicals materials, so we can design them to be safer at the first place without disturbing our ecosystem. And the challenge there, I want to speak a little bit about the challenge before I introduce what I plan to do is we simply really lack of toxicity and even the chemical characterization data, given the tens of thousands of chemicals and materials that we're using and we're releasing them to the environment accidentally. And as a society in general, I think our approach of mitigating those risks has been quite conservative, and we typically use it until there is has caused some ecological or public health crisis or consequences, then we are reacting to it and study them. So there are simply the data that we needed to assess their safety is severely lacking. And this is purely also speak of my own experience of studying thousands of chemicals used in hydraulic fracturing, which is unconventional oil and gas development. And without those data, we're unable to actually come up with design objectives to design those materials to be more sustainable in kind of forward thinking. So what we hope to develop is develop analytical and characterization tools to better understand their behaviors in the environment and assessing, so we can start to assess the ecological and health impact of some really critically important engineering polymer materials that are largely interact with our environment, and hopefully we can collaborate with the toxicologist on this work. And then we hope we'll be able to develop those multi-dimensional materials parameter space that would be able to incorporate both of the performance of the material as we are used to design and also the health considerations at the same time. So when you put those criteria together, we can start to delineate those trade-offs of materials design, including prices and performance, energy consumption, and health impacts of chemicals and materials. So ultimately, we can design chemicals, polymer chemicals that are safe at the first place.
Can I just jump in briefly to add a point that I should have made, which I'm sure all of us are thinking about, is that the impacts of climate change, right, they weigh more heavily on poor communities and of course on people of color as well, due to past practices in redlining, other racist histories in this country and around the world. And so I strongly believe that as we're setting up new systems and structures and infrastructure, technologies that we're thinking seriously about how to better serve those communities and right some of those wrongs as we go forward.
That's a great point. I just want to add that the blessing of that is that many of the poorest communities in the world have been dealing with challenges beyond our kind of imagination forever. And so they are masters at adaptation and at resilience. And so there's a lot to be learned from those communities as well.
Everything you guys have had to say is awesome, and I just really want to thank you all for being here. Our next question is, what is one of the most critical things engineers are going to be faced with in light of our changing climate? And we do have civil engineers, mechanical engineers, and advanced material scientists and engineers in this group. So.
Well, I can throw something out there. Regardless of which of those fields that Alison just walked through that you enter, what we're all going to be facing are questions from the communities for whom we are working, from clients that are buying our service, interested in our product, whether it's about material performance, it's about performance of a water system. People have questions about what's going to be changing in the future and how should we plan for that right now, and what we're doing in the planning for our community, in the planning for our process plant, in the planning for the material selection that we will be undertaking. What should we do? How are things going to change in the future that we might think about now, so that we have a robust design in whatever those domains it may be, and so that we spend our money cost effectively. We don't over design, but we don't want to under design, because that can have quite significant impacts on us, whether in any of those domains. So that a critical thing is answering those questions from the communities, the people we serve, the clients we serve. Those are tough questions.
I can add something. I just want to say that everybody here seems to be an absolute expert, and it's just cool to hear. So I consider myself very much generalist here, but I think one of the critical things that engineers are going to face is just resilience in the face of weather variability in general. We saw what happened when Texas got dumped on with a ton of snow, electricity grids went out. I'm here in the Twin Cities, and General Mills has a huge solar plant that was offline in Texas. And so it affects all of these systems. How can you design systems to be anticipating out of the norm weather and keep on going? And so lots of backups and resilience in the face of crazy weather coming up.
So I could add a sort of, oh, go ahead, Dave.
No, oh, okay. Well, I just was, now I've lost my train of thought. That's going crazy. Here's what it was. Stuart Brand, of the Whole Earth catalog, for those of us of that age, he wrote a book called How Buildings Learn, which I just love. And he really kind of talked about a building being kind of like a Russian doll with all these layers of systems that change at different rates. And you have some systems that are going to be there for the life of the building, 50 years or 100 years, and some things that are going to be there for the age of the carpet, which might be 5 years. And so we have to kind of rationalize how quickly those systems are in place for the change in climate or weather. Climate variability, which is relatively longer term thing, maybe doesn't affect the HVAC system as much as one might think if those systems have to be replaced in 15 years. And things like solar panels, we're doing a 115-acre site in St. Paul that's going to be all new. It was a golf course. It's going to have 1,000 jobs and 1,000 residents in it, but we got to figure out the best way to do it. It's going to take 10 years to build. What's happening 10 years from now that we should be designing into the master plan. You know, these are the questions that we have in order to try to make it work. How is equity going to work with this? How is things like increased ventilation rates for better cognition, you know, that we know is a thing, you know, how are we going to get people to think about that, consume a little more energy, have people be healthier, consume less healthcare, you know? I mean, I just think it's all complex, and there is no, to me, any one thing that we can attack in terms of changing climate, or we just have to have systems that are resilient enough to accept those changes, you know, that we can make them work, whatever's coming at us, because we're not going to know even what's happening next year. And I think this last year is what has proved that point.
I was going to discuss a one example impact that goes a little beyond the variability and, you know, weatherizing electrical generation equipment and that sort of stuff, which all needs to happen, right? But some of the work I've been doing in recent years looks at mass migration, right? We are going to have huge population shifts because of climate change, because people don't have water, because sea levels are rising. So what would you do if you're the city engineer? Say you've got 100,000 people in your town, and then, you know, next week you have an extra 30, 40, 50,000 people at your door, and they need housing, and they need water, and they need sanitation, and they need electricity, they need communication, they need all of this basic infrastructure, right? How do we do that? There are cities in Europe that maintain permanent housing stock to host asylum seekers. Maybe we need to go there, right? We're seeing this. We saw it as long ago as after Hurricane Katrina, when folks sort of picked up from New Orleans and ended up in Houston overnight, hundreds of thousands of new people. You know, there are climate refugees now from Pacific Island nations showing up in New Zealand and Australia. Well, not right now because of COVID restrictions, but have been for past years, right? This is something we are going to have to deal with as engineers, and it is an enormous challenge. I see some points in the chat pointing out some of this climate refugee stuff that's going on right now.
Yeah, I'd love to add, we're actually designing right now and starting a new school at Stanford on sort of sustainability and climate. The name has yet to be chosen, lots of contention around that. But it's been a really exciting process. And I think, so what I'm closest to in all of that is just the challenge of urbanization. There will be, the estimates are like 2 more billion people that will populate the earth before we kind of peak with our population, and almost all of them will be going into low and middle income country urban areas, which I think, again, something like 25% don't even have access to water. So there are just enormous challenges with how to design these cities. And they, in general, cities can be good. They are good. They provide paths out of poverty, but they also can be some of the most inequitable places on earth. So that's like such a challenge, and that we've been talking about a lot. And I think one of the things that's interesting for academics is coming up with solutions, particularly engineers, that actually will work and be implemented. And that just, it's a different kind of work. It's not, you know, we can publish our papers and then hope someone will pick it up. But if you really want it to be implemented, you have to kind of be on the ground working with the people that are going to implement it to get it to work. And it's much more of like co-creating solutions as opposed to like, I do my work here and I transfer it out, right? Outreach or something, you know. It's a different way of working, and in academics, you're not typically rewarded for that. And so we've been having a lot of discussions around how do we maybe change the way we reward that kind of work, you know, as professors and things. But I think it's really exciting if we can do more of that partnership for the students, for sure, who go out and practice right away, but also for those who become academics, just to have their work be implemented and have a larger impact. The one other thing around urbanization that I find so interesting is creating circular economies and how to like I have a colleague who, like I was talking about these plastics that we were making, that they biodegrade to methane. You use the methane to make more plastic, or you could use the methane for energy, or you can take wastewater and get the methane out of that and make plastic. So there's lots of different ways that these systems, water, energy, and yeah, just so many different systems and food can be integrated. I think it also can lead to more resilience instead of having lots of standalone systems. So there are just so many interesting interdisciplinary challenges that I think, yeah, just make this field really, really exciting. All the fields that you're in: materials, mechanical, and civil and environmental.
I really enjoyed hearing really large scale problems and sustainability challenges. I'll add a little bit more in the chemical and materials space that are, I think, perhaps more to the consumer goods space. I think the challenge there is to how do we design chemicals and materials for a certain intention, but without end up causing more problems, such as we use a lot of chlorination, but we end up having a lot of chlorinated disinfection byproducts. How do we prevent those events from happening? So I think designing a solution that is both environmentally benign and also as functional as what's demanded by the customers are going to be really one of the most critical things that we're facing the changing climate. There needs to be trade-offs of performances and environmental objectives are needed, and also really require us, completely change our way of designing our current products right now. And I think my perspective is, I think, maybe more on how we train our future engineers, which would include train them with their mind of circularity and sustainability, and always think about the entire life cycle of your products you design, and including the end of life cycle. And I think our current education is really, I think our engineers are really good at think about these solving problems for certain functions for a certain intended use. So if you think about linear economy, it would be the end. It would be at the end of the use phase. But where I think the engineers are much less aware or educated to think about the environmental impacts at the end of the life. That's why we've been designing a lot of products without knowing it can cause environmental consequences. So I think that's one of the most critically needed. And also on top of that, I think, as Sarah has mentioned, a lot of, this would be a very interdisciplinary challenge. We should also educate the engineers to learn to work with each other collaboratively on solving these problems, as we material scientists would have a certain skills that they all think about the design, certain design functions, and then environmental engineers think about, the natural environmental space. So how do we have them work closely with each other to come up with those materials that are both environmentally benign and functional at the same time?
I just have to jump in as a guy who I felt like I didn't really fit within the educational mold, or to some extent, I don't know. Yeah, didn't fit. I think that engineers are trained to be incredible problem solvers, but the engineering education is still getting to the point where you're teaching engineers to be researchers, problem identifiers, finding issues, understanding what is most important, defining them, and then turning those problems into opportunities for brainstorming and new ideas. The kind of role of the designer and the role of the engineer, I think, are merging a lot. So as engineering evolves, it'll get to a place where engineers aren't sitting waiting for a problem to be defined for them so they can solve it. They're out there finding the issues and trying things. So passionate about that side of it.
Me too. I have one little comment just to add to what Boya was saying about the thinking about the environmental impact as well as the function. And then also there's more thought also about the social impact. So there's like social LCA is my understanding. And I believe there's a gap in that there's stuff for products, so the social impact of the products, but not for like the operations. I think that's a really neat area I'm trying to get a student to work on. I don't know much about it, but look into it. Just like, you know, where are we getting the electricity from and what impact is that happening to operate our building over here? Like maybe, I think that could be pretty interesting to add.
Thanks so much for everyone's comments. This is awesome. We should be doing this all the time. But I want to open it up to questions from students or faculty that have joined us. What kind of questions have come to mind? You can just unmute yourselves and ask.
Suppose I could jump in. One that kind of jumped out to me from what David W. was talking about, kind of along the lines of